Hi, my name is Marcus Holzinger, and I'd like to talk about my research just a little bit to give you an idea of what it is we do in my lab. The main idea is that we focus on space domain awareness, or in other parlance, space situational awareness, sometimes also related to space traffic management, and it certainly all has applications to planetary defense with asteroids and stuff. So if I were to describe, what that is and what disciplines compose that body of study, I'd probably use, something like estimation, control, and dynamics as the basis for those activities, really sort of being wrapped by autonomy and decision support type studies. So the estimation stuff is largely about detecting and tracking things. The dynamics and control is about not just the astrodynamics involved, but in terms of actually controlling and guiding telescopes that have their own dynamics. There's a fair amount of work involved in reachability and optimal control. There's also work to do with autonomy and decision support. So asking how can we more efficiently collect information, or how can we provide higher quality data to decision makers so that they can render decisions. Those are all areas that we work in. And towards the end of this video, you'll see a number of smaller videos from each of my students and a description in their own words on what they're doing for their own PhD research. I want to talk a little bit about what situational awareness is, what space domain awareness is, and how that fits into multi-domain awareness. So situational awareness is fundamentally a local thing, and largely, if you can imagine that you're driving, it's your awareness of what's happening around you and what activities other drivers may be doing in the future and how that's going to interact with what you want to do in the future. The same idea extends to the space domain, right? So if we're talking about spacecraft operators, they certainly want to understand what other spacecraft are doing, what's happening in the environment, and they want to understand how it's going to impact what they would like to do with their own spacecraft in the future. That's a really local definition of space situational awareness. And when we start talking about space domain awareness, it's really a combination of a plurality of these individual situational awarenesses. And the domain, is often, in the current usage of the term, focused on a specific regime in which we're operating. So the space domain, the maritime domain, the aircraft, the air domain. And when we're talking about how all of these domains interact, that's when we get into something called multi-domain awareness. So largely the sort of scope of work that this lab focuses on is in space domain awareness, but there are naturally elements of it that tie into, for example, cyber-physical domain awareness and air domain awareness. So that's what situational awareness is and what multi-domain awareness is. I have a background in controls, and so I feel like I would be remiss if I didn't show a block diagram at some point. But what this is really a breakdown of Micah Ensley's situational awareness model and the different components in it. And so you can see how sensors might fit into this, how the actions we choose to task sensors and other things to do might fit in, where do the astrodynamics fit in, and then at the top, you see where much of the estimation, dynamics, control, autonomy, and decision-making sort of fit in. And when you write down a system in this block diagram, it becomes pretty clear that the problem of situational awareness, and certainly for space domain awareness in general, is really very similar to the problem of autonomy and distributed systems, as well as systems that have humans in or on the loop. So either in the loop, actively doing things like operators at an operations center, or on the loop in terms of decision makers trying to decide what to do about developing situations. So the work that we do is not just tied to dynamics, controls, and estimation. We have to have a broader view of the problem that also applies principles in autonomy, distributed systems, and human decision making. So we don't do human factors or cognitive engineering in this lab, but we absolutely collaborate with people that do to improve the problems, improve the solutions rather, that we pursue, and to improve the quality of our solutions to those problems. In terms of the current research portfolio, there are a whole lot more projects going on than what I'm just going to show in the next 2 or 3 slides. But overall, this should give you a good feeling. So we do a lot of low signal to noise ratio detection tracking, a lot of multi-target tracking. We absolutely task sensors to resolve individual hypotheses as opposed to just minimizing covariance of tracks. We've been working in uncued radio frequency or RF detection. We've done a lot of wide field of view imaging and image fusion. You'll see that a little bit later on. We've certainly worked with our telescopes to do closed loop tasking of low Earth orbiting space objects. We've worked on optimal set-based search and recovery. We've done set-based reachability computations for things like intercept sets or for custody questions in terms of, do we have custody of an object up in space? We've done attitude inversion of agile space objects. The idea behind that is, if you have an idea of what the shape model of an object is, and you know how bright it is over time, perhaps measured by a telescope, it turns out that you can back out what its orientation is and what it's looking at as a function of time. And this was something that we were able to demonstrate in a journal paper where we were able to use telescope observations of Hubble to identify which galaxy it was looking at a particular time. There's also a lot of other work that we do in initial orbit determination. In fact, this last year we won the best student paper award at the Amos conference in Maui. We've detected small micro debris objects using magnetometers only from the Themis spacecraft. And we've been getting into many of these autonomy and decision-making algorithms, for example, partially observable Markov decision processes. And we've been using those to great effect to investigate sensor tasking for not just Earth-based or Earth orbiting objects, but also for objects that are orbiting the three-body region or the four-body region in and around the Earth and the Moon. I have already mentioned that we collaborate with human factor studies. And so this is an example of one of those collaborations where we tested how well operators understand hypothesis-driven decision criteria versus covariance-driven decision criteria. Of course, the hypothesis one seems to do better in the testing we've done so far. We've done studies on both calibrating ultra-wide field of view sensors and extracting streaks from those sensors into time-resolved photometry. We've done a lot of work on optimal control-based maneuver associations. And certainly we've lately been focusing quite a bit on how to do initial orbit determination, tasking CONOPS, and catalog maintenance activities in the cislunar domain and identifying specific orbits that are very useful in those regimes. Finally, I'll leave you on the idea that this is not just a theory or a simulation lab. We do a lot of hands-on work with hardware. And we're in the process right now of installing a 0.6 meter telescope and a quad-mounted array of 4 0.32 meter telescopes. Combined, those are going to allow us to survey the geobelt about every 10 minutes and certainly take our own observations of objects near or around the Moon. So the wonderful thing about that is whatever theory we come up with, we can go through and apply it to software and then finally to hardware to validate our ideas. And that further improves the quality of our theoretical investigations because it tells us what sorts of problems we should be looking at to solve real, actionable problems.
Hey everyone, my name is Daniel Aguilar. I'm a fifth year PhD student here at the University of Colorado Boulder in Professor Holzinger's lab. I did my undergrad in the UK, and I did my master's at Georgia Tech, actually also with Professor Holzinger. And I moved here with him and some other students to CU Boulder. I've worked on various projects. Some of them are SSA related or space traffic management related. I've worked on things like telescope tasking and pointing control. Orbit determination and filtering has often been used for the sake of, maintaining situational awareness and inferring things about what space objects are doing and stuff like that. This has mostly been done in the sense of like custody maintenance and maneuver detection in my work, and how a lot of decision making and telescope tasking algorithms kind of play or sort of get coupled with the actual classification process. My thesis focuses on safe spacecraft formation flying, where we use things like model predictive control and reachability theory to make sure that spacecraft are passively or actively safe, as you can kind of see in these two figures.
Hi y'all, I'm Sam Fetteler. I'm a third year PhD student. I did my undergrad at NC State, and I'm a Draper and NSF fellow. Outside of class out here in Colorado, I enjoy skiing, brewing beer, and books. I focus for my research on Monte Carlo tree search and sensor tasking especially. We've looked at a variety of problems, especially catalog maintenance in the cislunar regime. How do we track a bunch of objects that we have previous estimates for at once? So that's been fun. I'm also looking at optimal follow-up tasking. So if we get an initial measurement on an object, where do we find it in the future when that initial measurement doesn't contain enough information to fully constrain the state of that object? So look forward to meeting you all.
Hey everybody, my name is Casey Heydrich. I am a PhD candidate at the University of Colorado Boulder, and I am also a graduate research and development intern at Sandia National Labs, New Mexico. My research involves atmospheric entry flight as well as guidance and control. In particular, I'm looking into advanced estimation and control strategies for reducing uncertainty during atmospheric flight. So previous studies of aero capture and other aero assist problems have developed vehicle concepts with high lift to drag ratios, which are less desirable from a risk and cost mission perspective. So some of the motivation for my research is reducing some of those requirements through advanced estimation and control strategies. So the program here is extremely good, and I would recommend any prospective students to take a look at our lab, and feel free to reach out with any questions. Thanks.
Hi, I'm Garrick Lau, and I am a first-year PhD student, and my research is on space object association. Oftentimes, observers will only be able to measure bearings only, and they won't be able to create, for example, range and range rates from the observation point to the space object. So this association algorithm creates these missile regions that contain possible range and range rates, and tries to associate two different sets of observation. And if those two observation sets seem to be associated, then it tries to create a full state of the space object.
Hello everyone, my name is Patrick Miga and I'm a first year PhD student in the Vader Lab. I graduated from Georgia Tech with a bachelor's degree in aerospace engineering. I'm a Matthew Isakowitz Fellow, and I came to CU to pursue my interests in astrodynamics. I'm still narrowing down my specific interests within astrodynamics, but I would like to focus on in-space infrastructure and the related orbits for commercial and defense applications. My current research focuses on observability in the cislunar domain. With the increase in orbital activity around the Moon, there is an interest in being able to observe a satellite quickly. Essentially, this boils down to being able to determine the states or position and velocity of the target satellite. My research is focused on figuring out the minimum amounts of time to minimize the uncertainty of these states based on location and orbit, and using this information to design configurations in which these are minimal. To do this research, I need to understand the circular restricted three-body problem in astrodynamics, as well as some controls and systems engineering. I mainly do this research by programming in MATLAB and interpreting the data, which is visualized in these images, but I also deal with some of the equations analytically.
Hi everyone, my name is Anna Montgomery. I'm a second-year PhD student. I graduated from the University of Florida in 2019. I'm an NSF and Draper Fellow, and outside of work, I like to spend my free time backpacking, skiing, and cooking, to name a few. So my research is focused on solving optimal control problems using continuation methods to smoothly transition between different objectives. So basically, given some initial and final desired state, how does the solution change as we transition between different costs that we're trying to minimize? In aerospace applications, these costs are commonly minimum time and minimum fuel. And so for me, I'm interested in applying this research to designing trajectories in the circular restricted three-body problem. And I'm so excited to meet you all.
Hello, my name is Karina and I'm working in constellation control for cislunar space. Right now I'm working on developing a station keeping control for repeating natural orbits such as the L1 and L2 Diapono family or the L1 and L2 Halo family. By being able to maintain a satellite for a long period of time in these type of orbits will allow me to generate patterns of life, where then I can analyze how often will maneuvers need to happen in order to maintain the desired trajectory. And I will analyze how my controller will perform against known or unknown disturbances, and in general, how it will behave within the dynamics of cislunar space. In addition, I'll be looking into a generalization of a control methodology in order to be implemented for different types of orbits. And in the future, I'll be working on generating control methodologies for constellations in cislunar space.
Hi, my name is Shez. I'm currently a fifth-year PhD student. I joined Dr. Holzinger's lab at Georgia Tech, where I got my bachelor's and master's in aerospace engineering. I'm currently funded by the NDSEC Fellowship, and outside of school, I enjoy building and messing with computers, coding, and photography, including astrophotography, and there's some really nice views in Boulder for it. One of my research topics includes multi-target low SNR detection and tracking, which is crucial for SSA. Here I'm showing images that I collected of geostationary satellites in a dark sky site, and the goal here is to get an output of something like this, where we're tracking all the objects in the frame and extract information like angle and angle rates so we can catalog unknown satellites, debris, find their orbits, see if they're maneuvering, etc. This is also very important for planetary defense community because they're doing the same thing, but for asteroids and comets. Another one of my research topics includes a novel orbit determination technique, including admissible regions, and we're trying to extend it to chaotic dynamics of cislunar space. And here I'm showing raw data of Chandrayaan-2 satellite on its way to the moon last year, and the goal will be to determine its trajectory as it was on its way to the moon using these techniques. And with that, I look forward to meeting with you all virtually. Thanks.
Hello, my name is Sam Bushlick, and I'm a fourth-year PhD student in Professor Holzinger's lab. My hobbies include making chainmail, and I'm trying my hand at brewing mead, and I want to see how that turns out. My research focuses on turning observations taken with a telescope into a full understanding of the object's orbit. My first major topic is a method for determining the distortion in an image due to the lens and removing that distortion for measurements. This is done using the locations of stars as reference points to determine the distortion. Next, there are times when we would benefit from knowing an object's brightness changes. To measure that, I have an approach for optimally breaking down a streak into segments so that the brightness can be measured to the highest accuracy possible without attempting to measure unobservable states. Then, I am working on approaches for estimating the full orbit of space objects using two observations. My research uses admissible regions to constrain a cost function for searching for the true state. This allows it to be reliably used in many more cases than existing methods.